All right, 15, we have a polling agency that conducted a survey by selecting 100 random samples, each one consisting of 1,200 US citizens. The citizens in each sample were asked whether they were optimistic about the economy. And for each sample, the polling agency created a 95% confidence interval for the proportion of all US citizens who were optimistic about the economy. Which of the following is the best interpretation of the 95% confidence interval? Okay, so a confidence interval, remember, is a range of values that we're we're confident that we have a strong belief that that it's going to contain the true population parameter. So that 95%, that means we're 95% confident that this interval will capture the true population parameter. In this case, it's the true proportion. Now, it's not like in terms of like probability, like mathematically, what does that mean? So that means that if we were to like generate, 100 of these confidence intervals using this method, we would have about 95 of them that would contain the true population parameter. Again, that's what probability is. If you did this, if you conducted this event multiple times, what percent or what proportion of the time would this happen? So let's look at these answers. With 100 confidence intervals, we can be 95% confident as a sample proportion. No, with the sample, like we know what the sample proportion is because that's what we get. And it's not helpful, so don't get tricked by that. They always throw these in here, so just be aware. I see a lot of these. B, we would expect about 95 of the 100 confidence intervals contain the proportion of all citizens of the U.S. who are optimistic about the economy. Okay, now this is what would be correct. We would expect about 95 of the 100 confidence intervals. That's what that 95% confidence means. Let me see if there's any other ones that maybe did not contain the sample. No, so B should be pretty straightforward. Like don't overthink this one because sometimes you make it, yeah. I've definitely made it more complicated than it needed to be. Anyways, 16. As part of a national sleep study, a random sample of adults was selected and surveyed about their physical activity and the number of hours they sleep each night. Of the 183 adults who exercise regularly, 59% reported sleeping at least 7 hours a night, at least 7 hours at night. Of the 88 adults who did not exercise regularly, 52% reported sleeping at least 7 hours a night. So which of the following is the most appropriate standard error for a confidence interval for the different proportions of adults who sleep at least 7 hours a night among exercisers and non-exercisers? Okay, so we have two groups. Let's call it N1. The first group has 183 adults, and that the proportion, we'll call it P1 hat, is 0.59. So 59% of them slept at least 7 hours a day. The other group and the second sample or the second group of adults is 88, has 88 individuals, and its proportion is 52% that slept at least 7 hours a night. Now we're looking at for the appropriate standard error. Remember, standard error is essentially a standard deviation or estimate of the standard deviation from sample data. So we have this in our actually formula packet. And it's actually, what do you know? It's the standard error of sample statistic. Since we have proportions, we're going to be looking at essentially this guy. Look, we have we're looking for difference in proportions. We got a difference right there. So nothing complicated. It's just this whole thing. So it'll be the square root, that P1 hat, that would make it 0.59. 1 minus 0.59 would be 0.41 over that group, 183, plus P2, 0.52 times 1 minus 0.52, so 0.48 over 88. Let's see what we got here. And bang, right away, it's the first one, it's A. The other ones, I think what they're trying to get at is when you, like the combined count, that's when you assume that That's when you're trying to test a significance test. When you're doing a significance test and you have to have the null hypothesis be that both groups have the same proportion of whatever it is. So don't confuse it with that. So the answer is A. 17. A representative of a car manufacturer in the US made the following claim in a news report. 10 years ago, only 53% of Americans owned American-made cars, but that figure is significantly higher today. A research group conducted a study to investigate whether the claim was true. The group found that 56% of a random select sample of car owners in the US owned American-made cars. A test of the appropriate hypotheses resulted in a p-value of 0.283. Assuming the conditions for inference were met, is there sufficient evidence to conclude at the significance level of alpha equals 0.05 that the proportion of all car owners in the US who own American-made cars has increased from what it was 10 years ago? Okay, so remember, we were in a significance test, we have an alpha level, and that alpha level, we set it to be basically what we want our probability or a p-value to be less than. So when we get a p-value less than our alpha, that's going to be what we call strong enough evidence to reject the null hypothesis and say we have, it's reasonable to believe the alternative is true. But our p-value is above this. Our p-value is greater than our alpha. When it's greater than alpha, that means we fail to reject HO. So then we can't really say we have any strong evidence that the difference that the proportion of car owners has increased from what it was 10 years ago. So it's going to be no. So it's going to be either D or E. And it's going to be E because we do it because it's greater than our alpha. This is our p-value. P-value has to be greater than alpha. So the answer is 17, or the answer to 17 is E. All right, 18. Researchers wanted to investigate whether babies have a sense of right and wrong. They showed each of the 60 babies a puppet show in which a red puppet was trying to open a heavy box lid. A second puppet called the helper would try to help the red puppet open the box, while a third puppet called the hinderer would try to slam the box lid down. After watching the show, each baby was presented with a tray containing the helper puppet and the hinderer puppet. And the researchers recorded which puppet the baby reached for. The researchers wanted to determine whether their babies would reach for the helper puppet more than the hinderer puppet. As part of the show, a green puppet and a yellow puppet served as the helper and hinderer. For each baby, a coin was tossed to determine which color would serve which role, or which color would serve which role. Which of the following is the most important reason for the random assignment of color to role in the study? Okay, so the reason we want to do random assignment when we conduct experiments is because we want to make sure there isn't any confounding variables or any variables or factors that might influence the results in one way or another. So we don't want to make sure our results don't become biased by this outside factor. So that's what random assignment helps take care of that to some extent. So in this case, we want to make sure that the color doesn't become a factor. So let's see which one best says that. Permits even more. The slamming the lid might cause the wear on the hinderer puppet. No. I get tired of showing the same. The random assignment of color keeps the push. No. Same rule, preference for color. Yeah, see, so this would be an example of a it would be C. That C because this is something that again might actually influence your results in one direction. So you want to make sure that if it doesn't, that it's not going to be one of the confounding variables. Let's see what the other ones would be. The random assignment of color to role allows the researcher to determine if one color. No, we don't care about that anyways. That's the thing. We don't want to determine if color influences it. Boys and girls might prefer different colors. The random assignment of color ensures that the show is equally accepted. No, because that's if you wanted to do that, you would break the group into strata, or break the population into strata. Have girls in one group, boys in another group, and then within each group, let's say girls and boys, you would have random assignment. You would have some of them, you would randomly assign within that group, or within each group, within the group. So then that way gender wouldn't be a factor. So you get 2 treatments, like treatment 1 and treatment 2 to each group. So the answer would be C for sure. All right.